Good evening, everyone. We are Team HICCUP. Our project today presents a model to predict intracranial hypertension within the next hour in real time, a critical yet tricky complication to model. Let's talk about Joe. Joe has just met with a nasty car accident and is currently fighting for his life in the neurosurgical ICU. Due to an overwhelming amount of medical information, doctors are at a loss for what to do. As a result, his doctors start to react reflexively rather than proactively in managing his dynamic physiological changes. Joe's brain starts to become edematous and swell. According to the Monroe-Kelly doctrine, his body attempts to maintain his ICP levels by draining its other components, such as blood or cerebrospinal fluid. However, Joe's rigid skull functions as a fixed volume container, and once compensatory mechanisms for intracranial pressure are exhausted, his subsequent rise in intracranial pressure occurs very rapidly beyond the potentially fatal limits of 22. Not noticing the subtle changes in the different parameters, Joe's ICP suddenly rockets. Without timely intervention, Joe starts to decompensate quickly. With high ICP or intracranial hypertension, Joe is at risk of rapidly developing devastating complications. How could we have done better? Our algorithm aims to make this a simple task to understand. To aid patients like Joe, we introduced HICCUP, a method of monitoring hourly ICP changes using a predictive model to predict episodes of intracranial hypertension. Our novel approach to ICP prediction allows for better adaptation and modeling of patient ICP values. This was done using discrete time interval values rather than ICP waveform data. Additionally, we also incorporated medical interventions into our models. Previous waveform-based models were severely limited due to their small sample size, complexity of interpretation, and lack of real-time applicability. Our recurrent neural network was built at a time series model that selected both static and dynamic data points, which were then analyzed by our model. We chose to train on the EICU dataset due to high granularity of data. Our team selected patients undergoing regular ICP monitoring, much like Joe. 863 patients with more than 100 ICP readings were chosen, with a total of 79 exclusions, leaving 784 patients for analysis. This resulted in a total of 1.77 million unique ICP readings, which was split into a training, validation, and testing set. This then underwent five-fold cross-validation. First, our team demonstrated on univariate analysis that ICH episodes were significantly correlated with hospital and ICU mortality, confirming the importance of predicting ICH episodes. Secondly, in our data exploration, we stratified our variables into two, static and dynamic, to better evaluate their relationship with ICH. For the static variables, we used random forest regression to identify pertinent factors correlated with ICH. Age, BMI, and admission GCS were identified. In order to address the non-physiological spikes present in the ICP data, an exponential moving average was used to reduce data noise. Missing data points were filled in using the last observation carried forward. Information was modeled and analyzed in 1.5-hour blocks to predict the occurrence of intracranial hypertension within the nearest hour. An ICP reading of above 22 was considered significant. We will now be presenting our results. We ran 3 models of HICCUP on the cohort with varying inputs. All 3 models had a similarly high AUC and correlation matrix. Using this model, we are able to predict Joe's ICP trends as shown here. Each bar represents 1.5 hours of data. The red color represents when ICP exceeds 22 within the next 1 hour, while the green bar represents no such increase. The bars above refer to actual values, while the bottom bar refers to the model's prediction. When the color of the top and bottom bars are the same, HICCUP has made an accurate prediction. However, the model has made a few false negative predictions. This may be potentially concerning and should be clinically correlated. To further improve these results, we ran our other 2 models on Joe's data. Our second model, which included dynamic variables, fared slightly better than the base, but our third model, which considered interventions at various time points, had fewer false negatives, thus showing its potential for more accurate predictions. Our model showed that it could incorporate timely management interventions that previous models had not considered. HICCUP could still adequately adapt to Joe's high ICP fluctuations and predictions in the next 1 hour. However, some interventions may precede patient ICP monitoring, affecting the patient's baseline ICP and hence the weightage of interventions in the model. Shapley analysis on dynamic variables were not performed due to time constraints. For future improvements, our team would ideally like to correlate with medical imaging, like results from CT scans or with other datasets. Furthermore, predicting 3- and 6-month functional outcomes, as well as mortality, would increase the clinical applicability of our model to patients like Joe. We hope that HICCUP will be a useful tool to aid clinicians in their management, reducing the missed ICH warning signs. In doing so, we hope to help Joe and many others from experiencing the devastating complications of ICH. Thank you.